All right, today we're going to go over section 8. We're going to go over all of it. I know some of it, maybe some of the, hopefully you were familiar with the information in section 1, mean, median, and mode, quartiles. We're going to go review all those ideas. I can go over any questions you have too. But originally the quiz was supposed to be on Thursday. It's going to be on Friday. Tomorrow we'll have a little time to go over anything. It's over section 7 and 8. The other reason I'm doing it on Friday is because 7th hour, I have a bunch of people down for track. It's just easier to have it Friday. Because most people should be here. I'm guessing you won't be here Friday. Is there golf? Okay, I just knew there was golf. Okay, so you'll be here. Good. Or is that bad?
Well, I'm not going to be.
You'd rather not be here.
I'd rather be here for the test.
Oh, would you? Okay. All right. Okay, so what we're going to do to review, kind of, like I said, I thought I could get you started in section 8 without me, and I'm guessing that went well. But if not, we're going to still review some things here. So realistically, what we're going to look at here to kind of review things, we're just going to use some data, and we're going to use it a bunch of different ways. Is we're going to look at question number 20A. Okay. And what it dealt with is finding just an average, a mean, and then also finding a weighted average. All right, so I want to look at that one together. We'll also find the median and the mode of that data set. So we'll talk about mean, median, and mode. Weighted mean, we'll also actually put it into quartiles. So we'll kind of review all those concepts that you should have read about yesterday. All right, so what that deals with is it deals with the monthly high temperatures in Beijing, China, and they're in Celsius. Okay, so if they seem small, that's because they're in Celsius. All right, so if we said month and we had the high temp, all right, I looked back to page 703, that's where it referred you to. I'm going to put the months as numbers. I'm not going to write them all out in words because I don't want to. 12, there we go. I didn't have enough room. And then the temperatures, like I said, I went and got those. It's 2. And once again, these are in Celsius. So if they seem odd, it's because they're in a different measurement than what we use here. Basically, the entire world uses Celsius other than pretty much us. 31, 27, 21, 10, and I'm going to put 3 here off to the side there. Now, if we wanted to find the average temperature, and this is in Beijing, China, okay, if we wanted to find the average temperature there, we could write this as a summation part if we wanted to, but the mean would be the summation of those temps divided by 12, wouldn't it? So you'd have to add all those numbers up and divide by 12. All right, so I'm going to do that here. We'll do this kind of carefully here. So we're at 7, we're at 19, we're at 39, we're at 66, we're at 97, we're at 129, and hopefully I'm doing this right. We're at 160, 187, 208, 218, 221. So I'm doing that in my head. You guys can always use a calculator or whatnot, but I'm going to get 221, and it's going to be divided by 12. That would give us our mean temperature. Okay, so what is that? What's 221 divided by 12? I'm going to use my phone. Part of decimals here. Actually, I'm going to use decimals. I'm using a calculator. All right, and once again, I may have added that up wrong. I did that fairly quickly in my head. All right, but it seems like a reasonable number. It's 18, 18.4. Okay, so that's how you find a mean. And you found averages before. This isn't anything new. Okay, this isn't anything new. Now I'm going to skip to the mode. If we look at these temperatures here, and once again, just realize I could have added that wrong. I'm not using a calculator to add those up, but I feel good about my answer, but we'll see. Maybe it's wrong. What would be the mode of those temperatures? First of all, what does the mode really represent? Mode is not the middle number. That's the median, right? The number that occurs the most often, right? Would that be, first of all, does a data set have to have a mode? No. Does this one have one? What is it? The mode is 31 because it shows up twice for both June and August. Once again, a data set does not have to have a mode. It can have more than one mode, right? In this case, we only had one. Okay. Now, the middle number, which somebody said, I think it was Maddie said, the middle number is the median. Now, in order to find the middle number, what should we do with these data values? Put them in order, okay? 2, 3, 5, 10, 12, 20, 21. Oh, are there two 27s?
Yes.
Okay, so we have another mode, sorry. There's two modes, okay? I didn't see that right away, but, all right, so we fixed it. And 21, then we are at, there's two 27s. There's two 31s. And then we have a 32. 2, 4, 6, 8, 10. I have my 12 data values. Now, since we have 12 data values, is there one true middle number? All right, I'm trying to make sure I'm recording this. There is not. There's two middle numbers, right? All right. So in order to find our median when we have an even set of data values, we have to look for the two middle numbers. Well, here's 1, 2, 3, 4, 5, 6. Are those the two middle numbers? All right. So to find our median, we're going to find the average of those two, and that's going to be 20.5. 20 plus 21 divided by 2. Okay. All right, so since there's 12 data values, an even number, there's not one true middle number. We find the average of the two middle numbers. If we had 13 data values, we'd end up with one true middle number. Okay. All right, so those are the basics for the measures of central tendency. Okay, those are kind of the basics there. Questions on that? Now, one of the other types of averages we find sometimes is called a weighted mean. Okay, it's called a weighted mean. Okay, now this data, we can find a weighted mean, and it's probably going to be a little bit different than this number right here. First of all, does anyone check to make sure I did this right? Is it 18.4? What's that? Okay, good. I feel good about that then, or that, or maybe we think alike. I don't know. Or we're that good, right? 18. Okay. You got the same total?
Oh, I didn't do that.
Yeah. Well, I'm more worried about the total. So if it's wrong, it's wrong. I'm not gonna dwell on that because nobody checked it for me. Now, a weighted mean. Why would we maybe find a weighted mean here? Because different months have different numbers of days, right? Right. That's where a weighted mean might pop up in this data set. So for example, the month of February right now is weighted the same as all those other months, but it has what? Fewer days. So its weight should be a little bit smaller, shouldn't it? Okay. Its weight should be smaller than that of, April or March, because they have 31 days. All right. So if we're going to find a weighted mean for this data, I'm going to go over to this next page here. All right. I would say that there are 31 days in January, right? Okay. 31 days in January, and the average temperature was 2. There are 28 days in February, easy for me to say. Okay, and that had an average of 5. And I would continue that process. March has 31 days. Its average temperature was 12. April has 30 days. Its average temperature was 20. May has 31 days. And there the average temperature was 27. The month of June has 30 days, and it had an average temperature of 31. I'm going to go down here. July, 7th month, has 31 days. The average temperature is 32. August has 31 days, excuse me, and its temperature was 31. September has 30 days, and the average temperature there was 27. October has 31 days, the average temperature was 21. November has 30 days, average temperature of 11, and December has 31 days, and the average temperature was 3. Okay, that's how we would deal with this weighted average. Okay, now instead of dividing this by 12 months, what would we divide this total by?
Wouldn't November be 10?
Was it 10? I wrote down wrong? Okay. Should be 10 right there. Yep, thank you. Okay, so instead of dividing by 12 like we did earlier, what are we going to divide by here? 365. Now, is this average going to be very similar to what we got earlier? Yeah, I'm pretty sure it's going to be very similar to what we got earlier. But this would be how we would come up with that weighted average. Different months have different number of days, so they would be weighted a little differently. Right? They would be weighted a little bit differently. Okay, and I'm not sure what that number should be here. I'm more concerned about the process than I am the number. The number should work out to be, should be right around 18.4 like the other one was, but probably not exactly. Okay, so I'm looking at my big answer key here. Unless somebody actually did the calculations, that would be good too. All right, so this is number 20. Yeah, the non-weighted was 18.42 like we did. This one's going to be 18.49. So it's not a whole lot different, but it is a little different, right? Okay. Basically, it's a little bit higher because of probably February is the one that really brings the average down. Does that make sense? Because it's weighted the same in our normal formula, but here's weighted a little bit different. So this should be 18.49. So it's not a whole lot different. The previous one was 18.42. All right, so this would be our weighted mean. Now, another application of weighted means would be maybe some classes you guys take. The teachers might grade things. They might weight categories differently. Does that make sense? For example, if you're in a class where tests are 70% of your grade and homework's 30% of your grade, right? Those are going to be weighted in that way. Okay, so you'd have to maybe use this type of formula to do that, to compute those. Now it's easy when you have a program like PowerSchool or even Canvas, they'll do the weights for you if you really want them to. In my class, it's total points, so it's not really weighted, basically. Okay. All right, questions on a weighted average or a weighted mean? That's generally one that pops up there. Now, the other thing that maybe you would have learned about yesterday when reading through that lesson was a 5-number summary. Okay, a 5-number summary for a data set is 5 numbers that will help us come up with a box and whisker plot. All right, it separates our data values into quartiles. 4 groups that should contain roughly 25% of the data values. Okay, now for our 5-number summary, here are some important numbers: the median, the minimum, and the maximum. Those are 3 that we can pick out right away since we already have the median. Okay, that's 3 of our 5 numbers: the minimum, the maximum, and the middle number. Now, then what we have to do is we have to find the median of the lower half and the median of the upper half. Well, if this is my lower half right here, there's 6 numbers. I think my median of my lower half would be right here, wouldn't it? So that would be what, 7.5? The average of those 2 middle numbers, right? And then on my upper half, I'm going to underline the upper half. I think my median should be right here. because basically there's 6 values above the median, 6 values below, so we have to deal with that even number idea again. So I think there our median of our upper half is called, or would be 29. Right? I'm not sure, some texts call those numbers different things. Did they call them Q1 and Q3 in the text? Okay. Q1 is the first quartile. All right, so basically Q1 would be 7.5. Our median is 20.5, and Q3 would be 29, and then we have our minimum and maximum. Those are circled there. Okay, so those are that's what they call them. All right, that's what they call them. Okay. I'm gonna write those down here. Because I'm going to make a box and whisker plot here too. Q1 is 7.5, Q3 is 29. Now, we can form a box and whisker diagram or box and whisker plot from those by basically putting that over a number line. All right. So I'm going to go from 0 to 40 because our temperatures all fell in there between 0 and 40. And kind of the first thing I'm going to do is make a little scale. You know, this would be 20, this would be 10. This would be 30. This isn't perfect. I'm just kind of eyeballing them in there. Then I'd have 5. Then I'd have 15. Then I'd have 25. Then I'd have 35. Now, a box and whisker plot is easy to construct. I need to basically plot out those 5 numbers. Well, here's our minimum. Here's our maximum, somewhere in that ballpark. Our median is right about here. Q3 is about right here. Q1 is right here. All right. So I just have to plot those 5 numbers, a 5-number summary, kind of above some kind of a number line. And once again, I went from 0 to 40 because that's easy to split up for me. All right. So here is what our box would look like. This isn't perfectly straight because I'm not able to do that. And there's our whiskers. Now, each of those 4 pieces, you know, these are our 4 pieces. There's 1 right here, 2, 3, and 4. Each of those 4 pieces should contain 25% of the data values. Okay, 25% of the data values. And since we had 12, that would mean each of them would contain 3 values. Okay. All right, we're splitting things into quartiles, 4 groups of 25%. Okay. So those are the concepts that you were hopefully looking at for today. Kind of getting going on your own. Anybody have any questions over that? We're going to start doing some new stuff now, but anybody have any questions over that? All right. Now, we also, rather than just talking about measures of central tendency, we also have measures of variation. Okay, we also have measures of variation. So I'm going to get to my PowerPoint here. And the first measure of variation is standard deviation. All right, standard deviation and variation, those 2 values measure the spread of data values. Okay. If we looked at the standard deviation of the ages of the students in this room, standard deviation would be small because you guys are all about the same age, right? You're all about the same age. Okay. If we did the standard deviation of all the people at the track meet tomorrow, it would be more spread out, right? Because you'd have adults, you'd have really young kids, you'd have old kids, you'd have high school age kids. Okay, it would be bigger. So it measures the spread. Okay. Now, we're going to go through and find the standard deviation of a data set here. And the variance. Basically, the variance and standard deviation are related. They are related. Okay. So we're going to find the standard deviation of those numbers we just looked at. The temperatures in Beijing, China, the monthly ones. Okay, I'm just using those data values again, right? But here's our formula. It says, realistically, I'll put the formula up here also again here in a minute, but and I'm maybe gonna write the formula in a little bit different way. Okay, just so you're aware of that. So here's the way I'm more familiar with that formula. All right, it's going to be the summation, and I got to make sure I do this right. I have to adjust it a little bit. From, they're going to say I equals 1 to n of x minus x bar squared over n. Okay. Now that seems complicated, but it's really not. Right? At first glance, it might look complicated. I better put x sub I here. X bar is our mean. Okay. So basically, we have to use that to find our standard deviation. Right? We're going to go through that process here. Now, remember, these were the numbers we had. So I'm just going to maybe make a table here. All right. I'll just put the temps in here. And it was 2, 5, 12, 20, 27, 31, 32, 31, 27, 21, 10, and 3. Okay. Now, you're probably going to want to pay attention here. You're probably going to want to have Desmos to help me with some of these computations. Now, we already found the mean. We found that earlier. That's x bar. We'll just say that that's 18.4. Okay. We already found that. We don't have to find it again. We could, if we needed to, add those up and divide by 12. So we're supposed to take, basically, this says take your data value minus the mean and then square it. So we're going to take 2 minus 18.4 and square it. Then we're going to take 5 minus 18.4 and square it. Then we're going to take 12 minus 18.4 and square it. 20 minus 18.4 and square it. 27 minus 18.4 and square it. 31 minus 18.4 and square it. 32 minus 18.4 and square it. And I'm just going to put a little arrow here that this number will be the same, right? Because I didn't leave myself enough room. I know this number would be the same, but now I have enough room to write the number here. 21 minus 18.4 squared, 10 minus 18.4 squared, and then 3 minus 18.4 squared, right? Basically, what we're doing in red there is we're finding all of these numbers right here. Okay. So maybe get your Desmos out here. What do we get if we take 2 minus 18.4 squared? I'm asking you guys to do that. So you can give it to 2 decimal places. That'd be good. What is 2 minus 18.4 squared? You're going to do this with a bunch of numbers here, so it should be
268.96.
268.96. All right, then what's 5 minus 18.4 squared?
179.56.
Say it louder, please.
179.56.
Then we have 12 minus 18.4 squared.
40.96.
40.96. 20 minus 18.4 squared.
2.56.
27 minus 18.4 squared.
73.96.
And I'm going to notice that I can put that down here, 96. 31 minus
158.76.
158.56.
76.
And that was 31, right?
Yep.
So that number can go right here too, 158.76. And then 32 minus that, 18.4 squared.
484.96.
How are you doing this so quick?
I just, in Desmos, I just
You
clicked
click it, okay. 184.1.
96.
Okay, thank you. 21.84. 21 minus 18.4 squared.
158.76.
And-
That's 31, sorry, 6.76.
And there's probably a way we can do this on Desmos a little bit quicker. And 10 minus 18.4 squared.
70.56.
70.56. And the last one, 3 minus 18.4 squared.
237.16.
All right, so we found all those. Now, this symbol right here says we should probably add all those up. So let's add all these up. Add those numbers up. I'm looking for a total there. And my writing isn't always easy to read, I know that, but I'm not great with an Apple Pencil. 2, 4, 6. And there are 12 numbers, so that's good. Hopefully more than one person's doing this so we can double check things. Question 20A, you weren't asked to do all this work, but we're just using those numbers as our data here. $1,456. Okay. Now, just to stop, look at the difference. This is the way I kind of write it. If you'd rather write it this way, that's fine. Because this is really kind of what we're doing, I guess. Maybe this makes more sense the way the book wrote it. Okay. And then we're basically going to divide those by 12. Because we had 12 data values, right? What is 1456.92 divided by 12? 121.41. Now, realistically, that's what we call sigma squared. This symbol right here is sigma. Sigma squared is our variance. Okay, if you look back to page 710, sigma squared is our variance. Just sigma by itself is the standard deviation. So in order to find that, we'd have to find the square root of that number, which is going to be 11 point something. 11 squared is 121, right? So it's easy to do in my head. It's 11 point what? What's the square root of 121.41? So I'm gonna go 0.2. We knew it was 11 point something. Like I said, 121 is an easy number to do in my head to estimate. Not like I would normally do that. So this is our standard deviation right here, and this is our variance right here. All right. It's a lot of calculations we're gonna have to do on a calculator. Okay, a lot of calculations we might have to do on a calculator. All right. Write those numbers down because we're going to maybe see if we can do that a different way. And hopefully we did it right. Okay. Now, I think we can do this on Desmos also. Now, I wanted to show you the long process. It's a longer process, but to be honest, nothing's complicated. We have the algebra, we subtracted, we squared, we divided by, I mean, it's not abstract algebra. you have to stay organized and you'd want to have your information very well organized. But if you go to, where do I have to go here? We did this the other day. Stats, okay, sorry. Is there standard deviation? Distribution. All right, where did we find that?
STDEV.
I think that might be it. Okay. And you can also see that there's mean, there's median, there's minimum, there's maximum. Some of those I don't know the median. Yeah, there's two of them. I was looking at this one, standard deviation. Now, let's see if we can use this right here. Now, I think what we have to do is put our data values in there. 2, 5. See, it starts building the standard deviation as we go. So I'm putting these numbers in here, and we'll see how that compares to what we did. Now, remember what we did, we rounded them off, right? So it might not be perfect. And I'm separating them by a comma. And hopefully I get all these values. Did I forget one? 5, 2, 5, 12, 20, 27, 31, 32, 31. Why are we so far off then? Because we got 11.02, right? Do you think that could be due to rounding? Seems like a lot. But... Go back here. What's that? Oh. What'd you get? Oh. Okay. Anyway, this is going to be more accurate. So we have that opportunity to do that. Okay. Do I have the right numbers in there? Let's make sure that 2, 5, 12, 20, 27, 31, 32, 31, 27, 21, 10, and 3. I think I do have the right numbers. Okay. All right, so you still have to plug those values in there. Okay. Now, not that we want to rely on this, but what if I went and put that mean out in front of there? Well, I did want to find the mean that way. Well, it did. Okay, so I just went back with the same data values and put the mean instead of standard deviation. That was the mean we got earlier, right? Okay. I'm going to go back and try one other thing just because. Let's try this one. Now, that's the number we got. Okay, there's 2 different standard deviations on Desmos there. Okay, that's the number that Maddie gave me, 11.018, right? So the difference between those two on Desmos is that standard deviation, STDEVP, is for a population. That other one is for a sample. We use the population one. So this is probably the one you're going to want to use. Okay. Like I said, I'm learning about Desmos as we go here too. Okay. So we didn't really do anything wrong. We had the right total. It's just that we chose the wrong option there. All right, we chose the wrong option there. Now, this is one of those times where doing this on a graphic calculator was easier than what we're doing here, I think, but it's just my opinion. Okay. Now, what other functions are there? You could find the median. You could, I mean, you could do all that stuff using this if you really wanted to. Okay. So there's other options, right? There are other options. All right. Okay. So that should be more familiar with standard deviation. Now, once again, we can review this stuff tomorrow. We're not, I mean, I was gonna have the quiz tomorrow, but I was gone, so we're not gonna do that. So there's that formula for standard deviation we should be familiar with. Remember, variance and standard deviation are related. Standard deviation is the square root of variance. Sigma and sigma squared. Okay. Now, last thing we're gonna look at today will be what's called a normal curve or a normal distribution. Okay. A normal distribution is something that's studied quite often, and sometimes it's referred to as a bell-shaped curve. Okay. Now, a normal curve is based off of both, kind of the spread, I should say, is based off of the mean and the standard deviation. Okay, the mean and the standard deviation. Basically, for a normal curve, I'm gonna use different color here. All right, this value right here should be our mean, which is also our median. Now, what the normal curve does is it bases everything on the fact that, like I said, it's a bell-shaped curve, that if we have a normal distribution, the data values should be spread out in such a way that we kind of have an idea of how well they're spread out. All right. For example, if we go one standard deviation above or below the average, you should have roughly 30 or 68% of your data values. Okay. All right. So think of it this way. If we think of the height of all the people in the United States as being normally distributed, okay, a lot of people would be right around average height. That makes sense? 68% of the people would be within one standard deviation above average and one standard deviation below average. Okay. Think of it this way. If this is our height, this would mean there's not a whole lot of really, really tall people, right? Because that goes down. And would it also mean there's not a lot of really, really short people? Most people would be around average. The farther away from average you get, the fewer elements that would be in there. Okay. All right. So 64% of the data values would be in there. Now, if we go out to 2 standard deviations, make this so you can see it, that should encompass 95% of the data values. All right. That should encompass about 95% of the data values. Okay. And if we go further, that's not the farthest we can go, but if we go to 3 standard deviations above and below, it should be 99.7% of the data values should be there. Now what I'm looking at is sometimes this is referred to as the empirical rule. It's on page 712. It's also the next slide here. All right, but I wanted to explain that with the diagram. Okay, so it says approximately 68% of the data lie between mu. Now, talk terminology here or notation. Mu is our mean. It's just a different variable used for the mean. So approximately 68% of the data lie between mu minus 1 standard deviation and mu plus 1 standard deviation. That's that range of 1 above and 1 below. Okay. 95% of the population should fall between 2 standard deviations below the mean and 2 standard deviations above the mean. And lastly, 99.7% of the data values should fall within 3 standard deviations of the mean, plus or minus. Okay, so basically the further away from average you get, the fewer elements that are going to be there. All right, the fewer elements that would be there. Okay. It's called a normal distribution. All right, now how can we use some of that? And once again, probably going to teach maybe up to the bell here because of yesterday, but once again, we have tomorrow to get caught up. Okay. This is that 68, 95, 99.7. So this would be a graphic of mu plus or minus 1 standard deviation. This would be a graphic for mu plus or minus 2 standard deviations. This would be mu plus or minus 3 standard deviations. Okay. Like I said, sometimes that's referred to as the empirical rule. Questions on that so far? All right, now let's look at using that in a problem here. Turn to page 715. We're going to look at number 41 here. Okay, 715, number 41. In 1995, scores for the Scholastic Aptitude Test, which is the SAT, were rescaled to their original mean of 500 with an approximate standard deviation of 100. Okay. SAT scores in the general population have a normal distribution. All right. So they're telling us that SAT scores, which means there's very few people that have a super high SAT score, and there's very few people that have a super small score. Most people are going to be about average, right? Okay, kind of like the example for height. So how can we use that? Well, they told us the average was 500 and the standard deviation was 100. Okay. Now we can use that 68, 95, 99.7 rule to answer some questions. Approximately what percentage of this 1995 scores fell between 400 and 600? Okay, so scores, what percent of the scores from 400 to 600? Now, in my thinking, 400 is mu minus a standard deviation, and 600 is mu plus 1 standard deviation. So should that be 68% using that rule we just discussed? Yeah, that should be 68%. 400 is exactly 1 standard deviation below, 600 is exactly 1 standard deviation above. All right, and once again, we're relying on this. Now, part B might throw us a little curveball here. Approximately what percentage of the 1995 scores fell below 300? Okay. So I'm going to put this up here. B, how many of the scores were below 300? Now, I'm going to actually draw this one out here. You don't necessarily have to, but I'm going to. All right. So we know 400 is, what is that going to be? Mu minus a standard deviation. So what does that mean about 300? What's that going to be? Mu minus 2 standard deviations. So realistically, we're trying to find out the percentage of scores that should be in this piece right here, which is sometimes referred to as a tail. Okay. What percentage of the data values should be in this tail right here? 2.5%. How did you get that?
95.
Yeah. Okay. If we look at the other half here, if we went to, this would be 600. This would be, oops, this would be 700. These two pieces, they don't look the same. Basically, didn't we say that 95% of our data values should be between here and here? We should have 95% in there, which means the two tails should add up to 5, right? And we're only looking for one tail. 5 divided by 2. That is exactly right. That is 2.5%. All right, so we're using that empirical rule a little bit differently. Okay, we knew that between 2 standard deviations above and below, we should be at 95%, which means there's only 5% on the far ends. 2.5 on each side. Okay, it would be 2.5 on each side. Okay. That's as far as we're going to go here. Okay, so that's how we can use that empirical rule. Once again, my curve there doesn't look perfectly bell-shaped. If it's perfectly bell-shaped, the mean and the median are the same thing. It has symmetry across that average or median. Mine doesn't look that way. Okay, so don't hold me to that.